Dijkstra. First talk for today is by Hannes Maynard. It's titled Leaving Legacy Behind. It's about the reduction of carbon footprint through microkernels in the Mirage OS. Give a warm welcome to Hannes.
Thank you. So let's talk a bit about legacy. So legacy, we have nowadays, we run services usually on a Unix-based operating system, which is demonstrated here on the left a bit, the layering. So at the lowest layer, we have the hardware. So some physical CPU, some block devices, maybe a network interface card, and maybe some memory, some non-persistent memory. On top of that, we usually run the Unix kernel, so to say, that is marked here in brown, which consists of a file system. Then it has a scheduler, it has some process management, it has a network stack, so TCP/IP stack. It also has some user management and hardware and drivers. So it has drivers for the physical hardware, for the network interface and so on. The brown stuff, so the kernel runs in privileged mode. It exposes a system call API or a sockets API to the actual application we are there to run, which is here in orange. So the actual application is on top, which is the application binary. It may depend on some configuration files distributed randomly across the file system with some file permissions and so on. Then the application itself also depends likely on a programming language runtime that may either be a Java virtual machine if you run Java, or a Python interpreter if you run Python, or a Ruby interpreter if you run Ruby, and so on. Then additionally, we usually have a system library, libc, which is the runtime library basically of the C programming language, and it exposes a much nicer interface than the system calls. We as well may have OpenSSL or another crypto library as part of the application binary, which is also here in orange. So what's the job of the kernel? So the brown stuff actually has a virtual memory subsystem, and it should separate the orange stuff from each other. So you have multiple applications running there, and the brown stuff is responsible to ensure that the different pieces of orange stuff don't interfere with each other, so that they are not randomly writing into each other's memories and so on. Now, if the orange stuff is compromised, so if you have some attacker from the network or from wherever else who's able to find a flaw in the orange stuff, the kernel is still responsible for strict isolation between the orange stuff. So as long as the attacker only gets access to the orange stuff, it should be very well contained. But then we look at the bridge between the brown and the orange stuff, so between kernel and user space, and there we have an API which is roughly 600 system calls, at least on my FreeBSD machine here in syscall. So it's 600 different functions, or the width of this API is 600 different functions, which is quite big, and it's quite easy to hide some flaws in there. And as soon as you're able to find a flaw in any of those system calls, you can escalate your privileges. And then you basically run in the brown mode, so in kernel mode, and you have access to the raw physical hardware, and you can also read arbitrary memory from any process running there. So now, over the years, it actually evolved, and we added some more layers, which is hypervisors. So at the lowest layer, we still have the hardware stack, but on top of the hardware, we now have hypervisor, which responsibility is to split the physical hardware into pieces and slice it up and run different virtual machines. So now we have the white stuff, which is the hypervisor, and on top of that, we have multiple brown things and multiple orange things as well. So now the hypervisor is responsible for distributing the CPUs to virtual machines and the memory to virtual machines and so on. It is also responsible for selecting which virtual machine to run on which physical CPU, so it actually includes a scheduler as well. And the hypervisor's responsibility is, again, to isolate the different virtual machines from each other. Initially, hypervisors were done mostly in software. Nowadays, there are a lot of CPU features available, which allows you to have some CPU support, which makes them fast, and you don't have to trust so much software anymore, but you have to trust then the hardware. So that's extended page tables and VTD and VTX stuff. Okay, so that's the legacy we have right now. So when you ship a binary, you actually care about some tip of the iceberg. That is the code you actually write and you care about. You care about deeply because it should work well and you want to run it. But at the bottom, you have the sole operating system, and that is the code the operating system insists that you need it. So you can't get it without the bottom of the iceberg. So you will always have a process management and user management and likely as well a file system around on a Unix system. Then in addition, back in May, I think there was a blog entry from someone who analyzed from Google Project Zero, which is a security research team, a red team, which tries to find a lot of flaws in widely used applications, and they found in a year maybe 110 different vulnerabilities, which they reported and so on. And someone analyzed what are these 110 vulnerabilities about, and it turned out that more than 2/3 of them, that the root cause of the flaw was memory corruption. And memory corruption means arbitrary reads or writes from arbitrary memory, which a process is not supposed to be in. So why does that happen? That happens because on the Unix system, we mainly use program languages where we have tight control over the memory management. So we do it ourselves. So we allocate the memory ourselves and we free it ourselves. That is a lot of boilerplate we need to write down, and that is also not a lot of boilerplate which you can get wrong. So now we talked a bit about legacy. Let's talk about the goals of this talk. The goals is on the one side to be more secure, so to reduce the attack vectors, because C and languages like that are from the 70s, and we may have some languages from the 80s or even from the 90s who offer you automated memory management and memory safety. Languages such as Java or Rust or Python or something like that. But it turns out not many people are writing operating systems in those languages. Another point here is I want to reduce the attack surface. So we have seen this huge stack here, and I want to minimize the orange and the brown part. Then, as an implication of that, I also want to reduce the runtime complexity, because it is actually pretty cumbersome to figure out what is now wrong. Why does your application not start? And if the whole reason is because some file on your hard disk has the wrong file system permissions, that is pretty hard to get across if you're not yet a Unix expert who has lived in the system for years or at least months. And then the final goal, thanks to the topic of this conference and to some analysis I did, is to actually reduce the carbon footprint. So if you run a service, you certainly that service does some computation, and this computation takes some CPU ticks. So it takes some CPU time in order to be evaluated. And now reducing that means if we condense down the complexity and the code size, we also reduce the amount of computation which needs to be done. These are the goals. What is a Mirage OS unikernel? That is basically the project I've been involved in since 6 years or so. the general idea is that each service is isolated in a separate MirageOS unikernel. So your DNS resolver or your web server don't run on this general purpose Unix system as a process, but you have a separate virtual machine for each of them. So you have one unikernel which only does DNS resolution. And in that unikernel, you don't even need a user management. You don't even need process management because there's only a single process. There's a DNS resolver. Actually, a DNS resolver also doesn't really need a file system, so we got rid of that. We also don't really need virtual memory because we only have one process, so we don't need virtual memory, and we just use a single address space. So everything is mapped in a single address space. We use a programming language called OCaml, which is a functional programming language, which provides us with memory safety. So it has automated memory management. And we use this memory management and the isolation which the program language guarantees us with by its type system. We use that to say, okay, yeah, we can all live in a single address space and it will still be safe as long as the components are safe and as long as we minimize the components which are by definition unsafe. So if we need to run some C code there as well. So in addition, well, now if we have a single service, we only put in the libraries or the stuff we actually need in that service. So as I mentioned, the DNS resolver won't need a user management. It doesn't need a shell. Why would I need a shell? What should I need to do there? And so on. So we have a lot of libraries, a lot of OCaml libraries, which are picked by the single service or which are mixed and matched for the different services. So the libraries are developed independently of the whole system or of the unikernel and are reused across the different components or across the different services. Some further limitation which I take as freedom and simplicity is not even we have a single address space, we are also only focusing on single core and have a single process. So we don't have a process. We don't know the concept of process yet. We also don't work in a preemptive way. So preemptive means that if you run on a CPU as a function or as a program, you can at any time be interrupted because something who's much more important than you can now get access to the CPU. And we don't do that. We do cooperative tasks, so we are never interrupted. We don't even have interrupts. So there are no interrupts. And as I mentioned, it's executed as a virtual machine. So how does that look like? So now we have the same picture as previously. We have at the bottom the hypervisor. Then we have the host system, which is the brownish stuff. Then on top of that, we have maybe some virtual machines. Some of them run via KVM and QEMU Unix system using some virt.io that is on the right and on the left. And in the middle, we have this MirageOS unikernels, where we in the host system don't run any QEMU, but we run a minimized so-called tender, which is this Solo 5 HVT monitor process. So that's something which just tries to allocate or will allocate some host system resources for the virtual machine and then does interaction with the virtual machine. So what does Solo 5 HVT do in this case is to set up the memory, load the unikernel image, which is a statically linked ELF binary, and it sets up the virtual CPU. So the CPU needs some initialization, and then booting is jumped to an address. It's already in 64-bit mode. There's no need to boot via 16 or 32-bit modes. Now, Solo 5 HVT and the MirageOS, they also have an interface, and the interface is called hypercalls, and that interface is rather small, so it only contains in total 14 different functions, which is main function yield, way to get the argument vector, clock, actually two clocks. One is a POSIX clock, which takes care of this whole time stamping and time zone business, and another one is a monotonic clock, which by its name guarantees that time will pass monotonically. Then you have a console interface. The console interface is only one way, so we only output data. We never read from console. A block device, well, block devices and network interfaces. And that's all the hypercalls we have. To look a bit further down into detail of how MirageOS Unikernel looks like, here I pictured on the left again the tender at the bottom and then the hypercalls, and then in pink I have the pieces of code which still contain some C code in a MirageOS Unikernel. And in green I have the pieces of code which do not include any C code, but only OCaml code. So looking at the C code, which is dangerous because in C we have to deal with memory management on our own, which means it's a bit brittle. We need to carefully review that code. It is definitely the OCaml runtime which we have here, which is around 25,000 lines of code. Then we have a library which is called nolibc. It is basically a C library which implements malloc and string compare and some basic functions which are needed by the OCaml runtime. That's roughly 8,000 lines of code. That nolibc also provides a lot of stubs which just exit or return null for the OCaml runtime, because we use an unmodified OCaml runtime to be able to upgrade our software more easily. We don't have any patches for the OCaml runtime. Then we have a library called Solo5 bindings, which is basically something which translates into hypercalls, or which can access the hypercalls and which communicates with the host system via hypercalls. That is roughly 2,000 lines of code. Then we have a math library for sinus and cosinuses and tangents and so on, and that is just the OpenLibM, which is originally from the FreeBSD project, and roughly 20,000 lines of code. So that's it. So I talked a bit about Solo5, about the bottom layer, and I will go a bit more into detail about the Solo5 stuff, which is really the stuff you run which is you run at the bottom of MirageOS. There's another choice. You can also run Xen or CubesOS at the bottom of a MirageOS Unikernel, but I'm focusing here mainly on Solo5. So Solo5 is a sandbox execution environment for Unikernels. It handles resources from the host system, but only statically. So you say at startup time how much memory it will take, how many network interfaces and which ones are taken, and how many block devices and which ones are taken by the virtual machine. You don't have any dynamic resource management, so you can't add at a later point in time add a new network interface. That's just not supported. Then, and at Mexico, much easier. We don't even have dynamic allocation inside of Solo5. Then we have a hypercall interface. As I mentioned, it's only 14 functions. We have bindings for different targets. So we can run on KVM, which is a hypervisor developed for the Linux project, but also for Beehive, which is a FreeBSD hypervisor, or VMM, which is the OpenBSD hypervisor. We also target other systems, such as Gnode, which is an operating system based on a microkernel written mainly in C++. VirtIO, which is a protocol usually spoken between the host system and the guest system, and VirtIO is used in a lot of cloud deployments, so it's okay. So QEMU, for example, provides you with a VirtIO protocol implementation. And the last implementation of Solo5, or bindings for Solo5, is seccomp. So Linux seccomp is a filter in the Linux kernel where you can restrict your process that it will only use a certain number or a certain amount of system calls. And we use seccomp, so you can deploy it without a virtual machine in the seccomp case, but you are restricted to which system calls you can use. So Solo 5 also provides you with the host system tender where applicable. So in the VirtIO case, it is not applicable. In the Gnode case, it is also not applicable. In KVM, we already saw the Solo 5 HVT, that is a hardware virtualized tender, which is, yeah, just a small binary, because if you run QEMU, it's, yeah, at least hundreds of thousands of lines of code. In the Solo 5 HVT case, it's more like thousands of lines of code. So here we have a comparison from left to right of Solo 5 and how the host system or the host system kernel and the guest system works. In the middle, we have a virtual machine, so a common Linux, QEMU, KVM-based virtual machine, for example. And on the right hand, we have the host system and the container. Container is also a technology where you try to restrict as much access as you can from a process. So it is contained, and the potential compromise is also very isolated and contained. So on the left-hand side, we see the Solo 5 is basically some bits and pieces are in the host system, so the Solo 5 HVT, and then some bits and pieces are in the unikernel. So that is the Solo 5 bindings I mentioned earlier, and that is to communicate between the host and the guest system. In the middle, we see that the API between the host system and the virtual machine, it's much bigger. That is commonly using VirtIO, and VirtIO is really a huge protocol which does feature negotiation and all sorts of things, where you can always do something wrong, like you can do something wrong in the floppy disk driver, and that led to some exploitable vulnerability, although nowadays most operating systems don't really need a floppy disk drive anymore. And on the right-hand side, you can see that the host system interface for a container is much bigger than for a virtual machine, because the host system interface for a container is exactly those system calls you saw earlier. So it's around 600 different calls. And in order to evaluate the security, you need basically to audit all of them. So that's just a brief comparison between those. If we look into more detail what Solo 5, what shades it can have, here on the left side, we can see it running in a hardware virtualized tender, which is you have the Linux, FreeBSD or OpenBSD at the bottom, and you have a Solo 5 blob, which is a blue thing here in the middle, and then on top you have the unikernel. On the right-hand side, you see the Linux seccomp process, and you have a much smaller Solo 5 blob. Because it doesn't need to do that much anymore, because all the hypercalls are basically translated to system calls, so you actually get rid of them. And you don't need to communicate between the host and the guest system, because in seccomp you run as a host system process, so you don't have this virtualization. The advantage of using seccomp is as well that you can deploy it without having access to virtualization features of the CPU. Now to get it in even smaller shape, there's another backend I haven't talked to you about. It's called the MUN. It's a separation kernel developed in Ada. So you basically, so now we try to get rid of this huge Unix system below it, which is this big kernel thingy here. And MUN is an open source project developed in Switzerland, in Ada, as I mentioned, and it uses Spark, which is a proof system, which guarantees then memory isolation between the different components. And MUN now goes a step further, and it says, oh yeah, well, you as a guest system, you don't do static allocations, and you don't do dynamic resource management. We as a host system, we as a hypervisor, we don't do any dynamic resource allocation as well. So it only does static resource management. So at compile time of your MUN separation kernel, you decide how many virtual machines or how many unikernels you are running and which resources are given to them.